Hello, this is a revision video for AP Chemistry, Chapter 7, Equilibrium. As this is a revision video, only the essential information is covered. For more detailed explanations and full video lessons, please check the links in the description below. Good luck revising.
Some reactions in chemistry are reversible. Reactants react to form products, but then these products can react again to reform the reactants. Where a forward reaction is considered as reactants being converted into products, and the reverse reaction is considered as the products going back to form the reactants. A system is in dynamic equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. Dynamic equilibrium can only be reached in a closed system, which is one where no matter can enter or leave. If a system is at dynamic equilibrium, the concentrations of all species remain constant over time, although it's important to point out that particles do continue to react. This is why it's referred to as dynamic equilibrium, because the reactions are still ongoing, particles are still reacting. It's just a system appears to us as unchanged because all the concentrations of species remain constant, hence equilibrium. Equilibria can involve either physical changes, like phase changes, or chemical reactions. In both cases, the forward and reverse processes occur at equal rates, but physical equilibria involve no change in chemical identity, whereas chemical equilibria involve the making and breaking of chemical bonds, forming new substances in each direction. For example, a container of water will undergo both evaporation and condensation. Now, if the rate of evaporation equals the rate of condensation, then the system would be at equilibrium. This would be a physical equilibrium because no chemical change is taking place. The Haber process would be an example of chemical equilibrium. Nitrogen can react with hydrogen to form ammonia, and ammonia can then re-react to form nitrogen and hydrogen. If the rate of ammonia production is the same as the rate of nitrogen and hydrogen production, then the system would be at equilibrium. This would be an example of chemical equilibrium because new species are being formed in each direction. Graphs can be used to show how chemical systems change over time as it approaches equilibrium. Whether we're looking at concentration, rate of reaction, or partial pressures, the overall pattern is the same. There's an initial change, followed by a steady state with no change. For a concentration versus time graph, the concentration of reactants decreases while the concentration of products increases. Once equilibrium is reached, both levels flatten out. They remain constant. Though remember, the reactions are still happening in both directions. For a rate of reaction versus time graph, initially, the forward reaction is faster than the reverse reaction. Over time, the reverse reaction speeds up as more product gets formed. At equilibrium, both rates become equal, meaning no net change occurs. The system is dynamic because reactions are still occurring, but balanced, hence equilibrium. For gaseous reactions, partial pressure versus time graphs follow the same pattern as a concentration time graph. The graph shows reactants' partial pressure falling and products' partial pressures rising until both level out, the partial pressures remain constant, and equilibrium is reached. In these examples, we have assumed that we have started with reactants going to form products for a forward direction, but it's important to remember that equilibrium can be established from either direction. You could also start with products and they would react to form reactants and still form an equilibrium system. In a reversible reaction, both the forward and reverse processes happen at the same time. The forward reaction involves reactants reacting to form products, and the reverse reaction involves those products reacting together to reform reactants. These two reactions compete, and the overall direction of change depends on which is happening faster. If the forward reaction is occurring at a faster rate than the reverse direction, the system moves towards forming more products overall. There is a net conversion of reactants to products. However, if the reverse reaction rate is faster than the forward reaction rate, the system is moving towards forming more reactants. There is a net conversion of product to reactants. Over time, the system naturally shifts towards a balance, where the rates of both processes become equal. This would be the establishing of dynamic equilibrium. For example, when hydrogen gas H2 and iodine gas I2 are first mixed together, they begin to react to form hydrogen iodide, Hi, in a forward reaction. At the start, the concentrations of H2 and I2 are high, so the forward reaction rate is much faster than the reverse reaction rate, which initially will be 0. HI starts to form rapidly, and there is a net formation of products from the forward reaction. As more HI builds up, however, it begins to react and decompose back into H2 and I2 through the reverse reaction. As more HI gets formed, the reverse reaction rate gradually increases. Eventually, the rates of the forward and reverse reactions become equal, because the forward reaction will start to slow down as H2 and I2 concentration decreases, but the reverse rate will increase because the concentration of HI has been increasing. At this point, the system reaches a dynamic equilibrium. The concentrations of all species remain constant, not because the reaction has stopped occurring, but because the forward and reverse processes are happening at the same rate. The reaction quotient Q is a snapshot of a reaction's progress. It is calculated by using concentration values of everything in a reaction mixture at a specific point in time. For the general reaction A plus B going to form C plus D, the expression for Q, the reaction quotient, would be concentration of C raised to its molar ratio in the equation, times by the concentration of D raised to its molar ratio, divided by the concentration of A raised to its molar ratio times the concentration of B raised to its molar ratio. So it's basically a way of expressing the ratio of products in the mixture compared to the concentration of reactants in the mixture. Note in these expressions, the square brackets mean concentration in moles per litre or molarity, M. The equilibrium constant K uses the same expression as Q, but only applies for a system when it is at equilibrium. Now, K is only valid for a given temperature and does not change unless the temperature changes. This sounds confusing, but what it really tells us is that when a system is at equilibrium at a specific temperature, the ratio of concentration of products to reactants in the mixture will always equal the value K. When writing expressions for Q and K, we only include gases and aqueous species. We don't include solids and pure liquids, because their concentrations can be considered constant, or more technically, their activities. The value of K tells us the position of equilibrium for a given system. So, for example, if K equals 1, the system is balanced. Neither the forward nor reverse reaction is favoured, so the concentrations of reactants and products are comparable. In other words, the position of equilibrium lies in the middle. If K is greater than 1, that means there must be a greater proportion of products in the mixture compared to reactants. In other words, the top of the fraction in the expression is bigger than the bottom of the fraction. This tells us that the equilibrium mixture contains a higher proportion of products than reactants, so we say the equilibrium favours products and the forward reaction is favoured. Equally, if the value of K is smaller than 1, this tells us the bottom of the fraction or expression is bigger than the top, so there is a greater proportion of reactants than products in the equilibrium mixture. We say the equilibrium favours the reactants, the reverse reaction is favoured. In simple terms then, the magnitude of K gives us an insight into which side of the reaction is dominant at equilibrium. The bigger the value of K over 1, the more the equilibrium favours the forward direction and the products. The smaller value of K under 1, the more the reverse reaction is favoured and the equilibrium favours the reactants. In the AP chemistry course, you encounter two main types of equilibrium constant: Kc, which is based on concentrations, hence the C, and Kp, which is based on partial pressures, hence the P. Partial pressures only apply for gases, so Kp can only be used for gas-based systems. Kp works in exactly the same way as the equilibrium constant for Kc. The total pressure of a gaseous system at equilibrium is directly related to the number of moles of each gas in the mixture. How much pressure one type of gas contributes to the total pressure of a gaseous system is called its partial pressure. All partial pressures of gases in a system add up to give the total pressure of the system. Partial pressures can be calculated using the mole fraction of a gas times the total pressure of the system. The mole fraction of the gas being the moles of that gas in the mixture compared to all moles of gas. So it's calculated by taking the moles of that particular gas and dividing it by the total moles of all gases in the system. We can compare the reaction quotient Q for a system to an equilibrium constant K to predict the direction in which a reversible reaction will proceed. This may sound complicated, but it really isn't that bad. If the value of Q equals K, then the system is at equilibrium. Because, remember, the value of K is the proportion of product to reactant concentrations at equilibrium, whereas Q is the proportion of product to reactant concentrations at any given moment in time. Well, if at any given moment in time the proportion of product to reactant concentrations gives the same value as K, then the system must be at equilibrium. However, if the value of Q for a system isn't the same as its equilibrium constant K, the system can't be at equilibrium, but the reaction will proceed in the direction that moves the value of Q towards K. So if Q is less than K, the reaction will shift in the forward direction, towards the product. Over time, this means the value of Q will get bigger until eventually it equals K and the system is at equilibrium. If the value of Q is greater than K, then the reaction is going to proceed in the reverse direction, towards the reactants. Over time, this will mean the value of Q gets smaller until eventually it equals Q, and then the system is at equilibrium. Exam tip here. It's really important to compare like with like when using Q and K. For example, if your equilibrium constant is a Kc value, then you must use concentrations for your Q expression, Qc. Equally, if your equilibrium constant is Kp, then you must use Qp values based on partial pressures. You can't mix Qc, for example, with Kp. The equilibrium constant K measures the ratio of products to reactants at equilibrium for a given reaction. For a reaction of A plus B going to form C plus D, the Kc expression, so equilibrium constant based on concentration values, will be concentration of C times concentration of D divided by concentration of A times concentration of B raised to their molar ratios in the balanced equation. The Kp expression, which would be an equilibrium constant based on partial pressures for a gas-based system, would be Kp equals partial pressure of C times partial pressure of D divided by partial pressure of A times partial pressure of B, again raised to the molar ratios given in the balanced equation. To calculate a Kc or Kp value, make sure you write the balanced equation in full, because this gives you the molar ratios and sets the exponents or powers for the K expression. Then construct the K expression using concentrations for Kc and partial pressures for Kp. Remember, if it's a gas-based system, you can use partial pressures, otherwise it must be Kc. Then substitute equilibrium values for each concentration or partial pressure, and then we can calculate as for any expression. Exam tip here, remember concentrations in the Kc expression and partial pressures in a Kp expression refer to equilibrium values. If a question gives you initial or starting concentrations, you can't simply substitute those into a Kc or Kp expression, because they aren't equilibrium concentrations, they don't refer to equilibrium amounts. Now, if a K value for Kc or Kp is very small, then that means very little product is present at equilibrium. Because of this, we can assume the reactant's equilibrium concentration is approximately its initial value. In other words, the concentration of reactant has changed so little that mathematically we don't really need to worry about it. The equilibrium constant K is a value that indicates the ratio of product amounts to reactant amounts in an equilibrium system. Kc referring to concentrations and Kp referring to partial pressures. If a value of K is very large, this tells us the numerator of the expression, so the top half, the products, must be much greater and bigger than the denominator, the bottom half, or reactants. So this shows us that the reaction goes nearly to completion. Your final equilibrium system contains very, very little reactant and mostly product. If, however, a value of K is very small, this tells us the numerator, so product amounts, is much smaller than the denominator, the reactant amounts. This tells us only a tiny amount of product has been formed. The equilibrium mixture contains primarily reactants, so the reaction hasn't noticeably occurred. If a value of K is 1 or very near 1, this tells us that the amounts of products to reactants in the mixture are roughly comparable, so neither the forward nor reverse reaction is favoured. Another way of looking at this is that the size of K indicates how far a reaction proceeded before equilibrium was established. established. So if K is very big, that tells us that the forward reaction rate was faster than the reverse reaction rate for a long time before the reaction rates became the same. In other words, more product got formed than reactant until the system got to equilibrium, meaning the equilibrium mixture contains a greater proportion of product compared to reactant. The equilibrium constant K is a value that indicates the ratio of product amounts to reactant amounts in an equilibrium system, Kc referring to concentrations and Kp referring to partial pressures. You need to know some basic rules for how K changes with certain manipulations. For example, reversing the reaction. If a reaction is written in the reverse direction, the equilibrium constant becomes the reciprocal. For example, for the forward reaction A going to form B, the equilibrium constant Kc would be concentration of B divided by concentration of A. However, the reverse direction, so B going to form A, would have an equilibrium constant Kc of concentration of A divided by concentration of B, or in other words, 1 over the Kc value for the forward direction. Multiplying a reaction. If all coefficients in a reaction are multiplied by a factor n, the new equilibrium constant is raised to the nth power. For example, for A going to form B, we've just seen the Kc expression would be Kc equals concentration of B divided by the concentration of A. So, for 2A going to form 2B, the Kc expression would now be concentration of B squared divided by the concentration of A squared, or in other words, the Kc value for the first reaction squared. Adding reactions. When two or more reactions are added together, the overall equilibrium constant is the product of the initial K values. For example, let's say reaction 1, A going to form B, has a Kc value of Kc1, and reaction 2, B going to form C, has an equilibrium constant of Kc2. For the overall reaction, A going to form C then, the Kc value would be Kc1 multiplied by Kc2. So the equilibrium constant for each reversible step multiplied together to give the overall Kc value. It's important to remember that the same rules that we've just used here also apply to Q, the reaction quotient, and Kc and Kp work in the same way as well. Exam tip here, don't forget that when working with Q and K, the concentrations used in a Q expression, so reaction quotient, don't have to be from when the system is at equilibrium. However, all values used for a K expression must be equilibrium values, so concentration for Kc or partial pressures for Kp. You may be asked to calculate the concentration of a species in an equilibrium mixture by using the equilibrium constant, Kc or Kp, and some given data. For example, calculate the equilibrium concentration of H2 for the following reaction. H2 plus I2 goes to form 2Hi, with a Kc value of 50 at 298 Kelvin. Now, if we assume that the concentration of Hi was 0 at the start, so we just reacted hydrogen and iodine together, the initial concentration of Hi will be 0. However, its change will be positive 0.8 molar. Because we know at equilibrium, its concentration is 0.8 molar. Equally, the I2 has an equilibrium concentration of 0.1 molar. Well, if Hi increased by 0.8 molar, then the concentration of I2 must have decreased by 0.4 molar, because the ratio of I2 to Hi is 1 to 2. So if the concentration of Hi increases by 0.8, the concentration of I2 must decrease by 0.4. This means the initial concentration of H2 will have decreased by 0.4 molar as well, because the ratio of H2 to I2 is 1 to 1. Now we have equilibrium concentrations in our table. Equilibrium concentration of Hi is 0.8, equilibrium concentration of I2 is 0.1, and equilibrium concentration of H2 is X minus 0.4 molar, because whatever the starting concentration was, it decreased by 0.4. Now we just need to substitute these values into our Kc expression to find the unknown X. So the expression will be Kc equals concentration of Hi squared divided by concentration of H2 times concentration of I2. We're told the Kc value is 50, so 50 equals the concentration of Hi, 0.8 squared, divided by the concentration of H2, x minus 0.4, times the concentration of I2, 0.1. With some rearranging, this will give us 0.1 times x minus 0.4 equals 0.0128. This can then be simplified down further to x minus 0.4 equals 0.128. So with some further rearranging, x equals 0.528. Now remember, the question was asking us for the equilibrium concentration of H2, which we said was x minus 0.4. So 0.528 minus 0.4 gives 0.128 molar. That would be the concentration of H2 at equilibrium. Now, if a K value for Kc or Kp is very small, then that means very little product is present at equilibrium. Because of this, we can assume the reactant's equilibrium concentration is approximately its initial value. In other words, the concentration of reactant has changed so little that mathematically we don't really need to worry about it. Particulate representations and diagrams can be used to help show the proportions of reactant and product particles changing as a system for a reversible reaction approaches equilibrium, given a visual indication to the magnitude of the equilibrium constant K based upon relative quantities of species. For example, before equilibrium is reached, the system will contain more reactant particles than product particles, and the reaction will proceed in the direction that reduces the imbalance between reactant and products until equilibrium is reached, or in other words, when Q equals K. Notice that you could also start with a mixture that contains more products than reactants for the reverse direction. Once equilibrium is reached, there is no net change in particle numbers. Both reactants and products are present, and their ratios match the equilibrium expression for the reaction and the value of K. Kc for concentration or Kp for partial pressures of gases. Now, if a Kc or Kp value is greater than 1, this means there's more product in the equilibrium mixture compared to reactant. So we'd expect to see more product particles than reactant particles. Equally, if the value of Kc is less than 1, there'll be more reactant particles compared to product particles in the equilibrium mixture. And if the value of K is equal to 1, then there will be equal or comparable amounts of both reactants and products in the equilibrium mixture. But it's really important to remember that in all of these cases, reactant particles are still reacting to form products, and product particles are still reacting to form reactants. It's just there's no net change in their concentrations. Exam tip here: when reading particulate diagrams, count species and relate them to the balanced equation. The ratio of products to reactants at equilibrium reflects the magnitude of K, not the drawing scale or particle sizes of each species. Le Chatelier's principle states that when a system at equilibrium is stressed, it will shift to counteract the stress and restore equilibrium. What this means is when a system at equilibrium is subjected to a change in conditions, the system will shift in the direction of reaction that will reduce or offset that stress, eventually re-establishing equilibrium. So the forward or reverse reaction will be favoured until the stress is reduced and a new equilibrium is reached. Exam tip here: you may see Le Chatelier's principle written in different ways, but always avoid thinking of equilibrium systems as trying to do anything. Le Chatelier's principle is observational. It doesn't explain why such shifting occurs. The reason these shifts do occur is because the rate for one reaction direction increases or decreases more than the other direction, meaning for a short period of time, both reaction rates in the equilibrium mixture are no longer the same, so it doesn't remain at equilibrium. Equilibrium is broken. After a given amount of time, the rates will become the same again and a new equilibrium will be re-established. However, now the quantities of all species in the mixture will have changed, hence we describe the system as having shifted and the equilibrium position having moved. There are several changes in conditions or stresses that you need to be aware of for AP chemistry. Effective change in concentration. If the concentration of a reactant in an equilibrium mixture is increased, the equilibrium shifts to the right. More reactants get used up, and the product concentration therefore increases. Hence, equilibrium shifts to the right, favouring the forward direction. If, however, the concentration of products in the equilibrium mixture get increased, now equilibrium shifts to the left, meaning reactant concentration will increase and the product concentration will decrease. Reverse direction has been favoured. Note in both of these cases, the equilibrium constant Kc or Kp will remain unchanged. For example, for the equilibrium system A plus B going to form C, if more A gets added to the equilibrium system, equilibrium shifts to the right, which means more C will get produced and the concentration of A and B will decrease slightly until a new equilibrium system is established. Effective change in temperature. If the temperature of an equilibrium system is increased, the endothermic direction will be favoured, and equilibrium will shift in that direction. Equally, if the temperature of the system is decreased, now the exothermic direction will be favoured and equilibrium will shift in that direction. For example, in the Haber process, the forward direction, so nitrogen plus hydrogen to ammonia, is exothermic. So, if the temperature of the system is increased, equilibrium will shift to the left, favouring the endothermic direction, which would be the reverse direction. So, the concentration of ammonia in the mixture will go down, but the concentrations of nitrogen and hydrogen will increase slightly until a new equilibrium is established. Note, however, that the value of Kc and Kp will change when the temperature is changed, because K, the equilibrium constant, is dependent on temperature. So in our Haber process example, because the forward direction is exothermic, increase in the temperature shifts equilibrium towards the reactants, so K would decrease, because the new equilibrium system will have a slightly higher proportion of reactants compared to products than before. Equally, because the endothermic direction is the reverse direction, if we increase the temperature, we shift the equilibrium towards the products, meaning K will now increase, because the new equilibrium mixture will contain a slightly higher proportion of products compared to reactants than before. Changing pressure for gaseous-based systems. If a gaseous-based equilibrium system has its pressure increased, the equilibrium will shift towards the side that produces the fewest moles of gas. Equally, decreasing the pressure will shift the equilibrium towards the side that produces the most moles of gas. If the moles of gas produced by both reactions are the same, changing the pressure will have no impact on the equilibrium position. Notice again that change in pressure will have no effect on the value of Kc or Kp, because only temperature changes the value of the equilibrium constant. For example, in the Haber process we've just looked at, there are 4 moles of gas on the left-hand side, the reactants, but 2 moles of gas on the right-hand side, the products. So if the pressure of the system is increased, the equilibrium position will shift to favour the direction that produces the fewest moles of gas. In this case, the forward direction, meaning the concentration of ammonia will increase slightly and the concentration of nitrogen and hydrogen will decrease slightly. Catalysts don't affect equilibrium position or equilibrium constants, K. The rates of the forward and reverse reactions are increased equally when a catalyst is added to the system. As a result, a catalyst simply helps the system reach equilibrium faster, but it doesn't affect the proportion of products to reactants in the mixture once equilibrium is reached. Le Chatelier's principle describes how a system at equilibrium responds to stress. The reaction will shift to oppose the change and re-establish equilibrium. We can predict the direction the system will shift in by using the reaction quotient Q for the reacting system and the equilibrium constant K for the reaction. Remember, K, the equilibrium constant, Kc or Kp, is the ratio of product to reactant concentrations at equilibrium, whereas Q, the reaction quotient, is the ratio of product to reactant concentrations at any moment in time, even if the system isn't at equilibrium. When a system is disturbed or stressed, if the reaction quotient Q is smaller than K, the system will shift right to form more products, and Q will slowly get bigger again until it equals K and the system is at equilibrium again. If the value of Q is greater than K, the system shifts to the left to form more reactants. The value of Q gets progressively smaller until eventually it equals K and the system is at equilibrium again. Remember, when Q equals K, the system is at equilibrium. So if a system at equilibrium is subjected to a change or stress, but Q continues to equal K, then no shift will occur. Exam tip here, you can kind of think of Q as telling us where the reaction system is at any moment in time, and K telling us where it's going to go. So Q being the ratio of product to reactant concentrations at a given moment in time, and K being the proportion of product to reactant concentrations at the end, when the system reaches equilibrium. So how does this link to Le Chatelier's principle? Well, when a system at equilibrium is disturbed, what we really do is we change the value of Q compared to K. For example, if a reactant is added to a system at equilibrium, the denominator in the Q expression increases, meaning the value of Q decreases. And as we've just seen, this means equilibrium will shift to the right. Equally, if a product is added into a system at equilibrium, the product concentration increases, so the numerator in the Q expression increases. This means Q increases in value, and as a result, equilibrium shifts left. Changes in pressure and volume for gas-based systems affect QP in the same way as QC. Temperature changes are slightly different because they actually change the value of K rather than Q. For example, for an endothermic reaction direction, increase in the temperature increases the value of K. The system shifts to the right. For exothermic reactions, increase in temperature decreases K and the system shifts to the left. When the temperature is initially changed, Q remains the same because we aren't changing the concentration of products or reactants, we're just changing the temperature. But because K has changed, the system is now out of equilibrium. Q doesn't equal K. And as a result, the concentrations of everything in the system will have to change to make sure Q equals K again. And now we can predict the change that will occur based upon the same rules as before. If Q is smaller than K, equilibrium will shift to the right, favors the forward direction, or if Q is greater than K, equilibrium will shift to the left and favor the reverse direction. KSP is the solubility product constant. It shows the equilibrium position of a dissolving ionic compound. It is an equilibrium constant that works in a similar way to Kc and Kp, but with a few exceptions. When an ionic salt dissolves, it breaks into its ions. For example, the solid AB solid can break apart into A+ and B- ions. They will be given the state symbol AQ to represent they are dissolved in water. When a salt is partially soluble, only a small proportion of its ions are dissolved in water at any one moment in time, meaning some but not all of its ions break away into solution. Now, the process of dissolving is reversible. As ions dissolve from the solid into solution, dissolution, some also recombine to reform the solid salt, precipitation. Because of this then, when a solid dissolves in water, some ions are constantly breaking away and entering into the solution, but also some ions from the solution are recombining to reform the solid. Eventually, the solution reaches a point where the breaking away of ions, so dissolution, equals the rate of solid formation, so precipitation. At this stage, the system is at equilibrium and the concentration of dissolved ions stays constant, even though the solid is still present. We can describe this equilibrium using the solubility product constant, KSP. It reflects how soluble a salt is. A higher KSP value means greater solubility, while a lower KSP value indicates that only a small amount of solid is dissolved at any one moment in time, so a very low solubility. To write a KSP expression for a given salt, we first must write out the reaction. So for the example just given, AB solid goes to form A+ aqueous plus B- aqueous. The KSP expression then would just simply be KSP equals concentration of A+ times concentration of B-. Because remember, we don't include solids in equilibrium expressions. For salts with multiple ions of the same type, we need to include coefficients as powers in the expression. For example, calcium fluoride, CaF2, would have a KSP expression of KSP equals concentration of Ca2+ times concentration of F- squared. This is because if we look at the equation for the dissolution of calcium fluoride, we see it CaF2 goes to form Ca2+ aqueous plus 2F- aqueous. The 2F- aqueous needs to be reflected by squaring the concentration of F- in the KSP expression. Molar solubility refers to the number of moles of a substance that dissolve in 1 liter of solution to form a saturated solution. Essentially, it is a measure of how much solute can dissolve under equilibrium conditions. As we've seen, the solubility constant, KSP, tells us how soluble a salt is in water, but care must be taken when comparing values. If the stoichiometry for different salts are the same, we can compare KSP values directly. For example, for AgCl and NaBr, the salt that has the higher KSP value will be more soluble, because both salts just simply contain ions in a 1-to-1 ratio, so the one that has the higher KSP value is the more soluble salt. However, if the stoichiometries of two salts are different, we can't use KSP values directly to compare their solubility. Instead, we have to compare their molar solubilities. For example, for calcium fluoride CaF2 and AgCl, because the salts contain different ratios of ions, 1-to-2 in CaF2 and 1-to-1 in AgCl, the fact that CaF2 has a larger KSP value than AgCl doesn't automatically mean it's more soluble, because we haven't accounted for the fact that there are actually more ions present when 1 mole of CaF2 dissolves compared to 1 mole of AgCl. As a result, we have to calculate their molar solubilities, so the number of moles of the salt that dissolves per litre of water, before we can compare the salt's solubilities directly. Exam tip here, this is a really key rule to remember. If salts contain the same ion ratios, then you can compare their solubilities directly using KSP values. However, if the salts contain different ion ratios, then you first must calculate their molar solubilities in order to determine which one is more soluble. Common solubility rules can be explained using KSP values. For example, all salts that contain sodium, potassium, ammonium, and nitrate ions are soluble in water, and these salts correspond to very high KSP values. Equally, salts that have very low KSP values indicate low solubility, so compounds are often called insoluble in practice, even though a tiny bit of that salt will still dissolve in solution. Because it's such a small proportion of dissolved ions compared to solid, we consider them to be insoluble in the everyday world. When a salt is added to a solution that contains one of its own ions, its solubility decreases. This is known as the common ion effect. For example, silver chloride AgCl dissolves in solution to release one silver ion, Ag plus aqueous, and one chloride ion, Cl minus aqueous. Normally, a small amount of AgCl dissolves until the system reaches equilibrium, so remember, the rate of solid dissolving equals the rate of ions recombining to reform the solid in precipitation. But if the solution already contains chloride ions from another salt, such as sodium chloride, these extra Cl- ions shift the equilibrium of the solid dissolving to the left, according to Le Chatelier's principle. This effect can be observed when two saturated solutions, one of sodium chloride and one of silver chloride, are indeed mixed. Treating the dissolving of the AgCl as an equilibrium system, we can see that the added Cl- ions from the NaCl solution increase the product concentration for the equilibrium system. Well, according to Le Chatelier's principle, the system will respond by shifting the equilibrium position to the left, reducing the concentration of ions in the solution, and as a result, forming more solid AgCl. Because of this, a visible precipitate of AgCl will form. This common ion effect is really important when predicting how soluble a salt will be in the presence of other dissolved substances. Even without full calculations, you can explain the common ion effect using equilibrium principles in Le Chatelier's principle. Effectively, adding more of a product ion, like the Cl- ion in our AgCl example, drives the system to form more solid and reduce the concentration of ions in the solution, ultimately decreasing the salt's solubility.